Okay. So new stuff. So recall, if I ask you this question, you will not have any problems telling me what that equals to, right? Hopefully. What is that equal to? 9. Now, what we're going to start today is kind of the opposite operation. We're going to discuss square roots and all those other so-called radicals. So the square root, that's the first one we're going to look at. I'll ask you a question like that. Square root of 9. And, most of you have seen that before. What do you think that equals to? 3. Why is that 3? What? No. But some to do with the square. But we only chose positive 3, because technically negative 3 should work as well. Negative 3 squared is 9, but we just defined the square root to be a positive item. Okay? So a little bit of notation. This squiggly thingy, we call that a radical sign. The number underneath is called the radicand. And we define the principal square root the following way. The square root of a is always positive. So the square roots cannot produce negative results. And 2, square root of a equals b implies that b squared equals a. So the square root has to meet these two definitions. It has to stay positive. And if you square the result, you get the radicand back. So just like here, if you square 3, you get a 9. And 3 stays positive. Square root of a equals b implies that if you square b, you get a back. You get the radicand. But anyways, you understand how the square roots work. The big thing here is to realize it always stays positive. Okay, square roots do not produce negative results. So a few examples. I'm just going to write a bunch of little expressions. We're going to try to evaluate them. So for example, how about the square root of 4? What do you think that equals to? 2. And why is that? And what else? 2 squared is 4. What else? It's positive. Right. It has to be positive. Because negative 2 squared is still 4. But we want the result to be positive. How about square root of 49? 7. Good. How about the square root of 1/4? 1/2. Because 1/2 squared equals 1/4. How about square root of 1/16? 1/4. How about square root of 1? 1. How about square root of 0? 0. Right? Does that fit our definition? Well, definition states the square root is greater than or equal to 0, so that works. How about square root of -4? What? Well, what is 2 squared? Right, so there's no real number such that if I square it, it'll give me negative 4. So this is not a real number. Right? But what if I ask you, what is negative square root of 4? Negative 2, because that negative has nothing to do with the square root. That really means negative 1 times the square root of 4. And square root of 4 is 2, so we end up with negative 1 times 2, or negative 2. So the square root still produced the positive answer, but the negative sign was there to begin with. There's nothing we can do about that. But what if I ask you negative square root of negative 4, like that? Can do it. So we cannot distribute the negative under the radical, so it's just negative 1 times the square root. That's not a real number, so still not a real number. Okay? Now we understand what I mean by a real number, right? Have we had our talk about real numbers? No, it was probably during first week or two. Did we talk about natural numbers and rational numbers and yeah. But anyway, so the structure, basically the real number is anything that you can, every number that you've ever seen was a real number, okay? And we use this letter to represent set of real numbers, and real numbers, they live on a real number line, okay? So they all belong on that thing. So you have your 0, and you have your integers, and you have your fractions in between integers, and then you have the irrational numbers in there too. But the way we dissected that, we had a set of natural numbers, so we use the letter n like that to represent set of natural numbers, and those are your counting numbers, 1, 2, 3, and so forth. Those are all real, the positive integers. Then we also had set of integers. We use letter z to represent that. Now the integers are just positive and negative whole numbers. Natural numbers are strictly positive. Yeah. So 0 is not a natural number in 90% of the books. Then we looked at set of rational numbers, integers. What? Yeah, z with a little extra kind of a twist, kind of a double line here in the middle. Just a weird fancy z. Now, set of rationals, those are your numbers that can be expressed as a ratio of two integers. No, I'm about halfway through that. So I haven't put any grades online yet. I'll just wait till I finish it. So the rational numbers are your fractions, and we use letter Q with a little twist. Not really. It's just we use those to represent those specific sets. So now, as long as you can write a number as a ratio of two integers, that's a rational number. So things like 1/2, -7/8, those are rational numbers. Number 5, all your integers are rational because you can always say 5/1, 10/2, and so forth. So 3 2/3, blah, blah, blah. So all of those, they're infinitely many of those numbers. So this is kind of a structure that every natural number is an integer, and every integer is also a rational number. So they're all kind of one inside the other. But then the final kind of partition on real numbers is the set of irrational numbers. And those numbers that cannot be written as a ratio of two integers. We don't have a fancy symbol for those, but basically, pi is one of those. And since we're getting into square roots, numbers like square root of 2, square root of 3, those are all irrational. I can never be able to express square root of 2 as a ratio of two integers. Any combination of them, let's say square root of 2 plus 5/7, that's irrational. Square root of whatever you want, 21. When we get to high radicals, cube root of 2 is irrational and so forth. So all those just give you a crazy decimal that has no pattern, no repetition in it. So we'll be focusing on these numbers now. We're going to be looking at properties of square roots of 2s and square roots of 3s and how we can manipulate them, because as far as I'm concerned, square root of 2 equals square root of 2. I don't care what it equals to as far as the decimal goes. Square root of 2 is square root of 2. There's nothing else you can do about that. Okay? It has some decimal value, 1 point, I don't know, something. If I take the square root of 2, something like that. So, but I don't care. Square root of 2 is square root of 2. Okay? So you don't. So you put all that together, that's a real number. And if we go to things like that, square root of -4, that's not a real number. It does not belong to any of our sets here. Okay? It does not live on that number line. It lives somewhere else. We don't need to know that yet.
So you're saying that all of these are real numbers?
Yeah. It's just I'm kind of partitioning the set of real numbers, classifying them. So if I say a rational number, you should think, okay, something nice and pretty, maybe a fraction. And when I say irrational number, you start shaking because they're just ugly and hard to deal with. Okay? Rational is good, irrational is bad. That's kind of the big message. Okay? So we don't really like irrational numbers. We'll discriminate against them freely in this class. Yeah. So the square root of 2 does live somewhere here. Pi lives somewhere there. So I can still locate those numbers on the number line. So they're real. This would be the square root of 2. This would be pi. So they all belong there. Okay? It's there is an answer for that. We had to come up with a whole Just like at some point you felt like you needed -4, just a negative number. If you think about this, -4, that's a made-up number. If you think, right? Just think about this. Well, what does that mean, -4? I mean, you're okay with -4. You've seen negative numbers all your life. You're not freaked out by negative numbers. Well, you have to expand your imagination a little bit to buy into the idea of a -4. Yeah, so that's what square root of -4 would be. So we had to do that again. We had to expand our imagination to include those numbers to make some things work out. And then that wasn't enough, and we kept expanding and expanding. Creative people, that's right. Right, because these are real numbers. What Nick was saying, there are imaginary numbers. There are also surreal numbers. There are hyperreal numbers. Well, yeah, there are magical numbers, but they're just cool. They're still real, but there could be like a set of kind of weird numbers that have some interesting properties. But anyways, don't worry about that. Real numbers. That's all you need so far. Okay. All right. So a little bit on notation. Recall when we say mixed numbers, things like 3.5. Okay, so that's a mixed number, right? Well, what does that mean? 3.5. What does that equal to? 3.5, right? It's really this. There's a silent plus that literally means 3 plus 1/2. It's 3.5. Okay. While here, when you see things like 2 square roots of 3, that is equivalent to this notation, 2x. Here it's a product. Okay, so it's different from the mixed number. It really means 2 times the square root of 3, just like you have 2x. It implies a product. So it's 2 square roots of 3. It's not 2 and square root of 3. If I want to do that, I'll literally write a plus, 2 plus square root of 3. So there is a little, could be a source of confusion. Maybe if I never mentioned that, it would never been a source of confusion, but now you know. So, okay. Right, so it's just 2 times x, or 2 times square root of 3. So you have a total of 2 of those. Like here, doesn't mean you have 3 halves. It's 3.5. Right, so that's kind of different, but at the same time similar notation. So anyways, so let's play a little more with these numbers. What do you think? So play some more. That's what we're doing. What do you think will happen if you take a square root of 4 and then you square all of that? What do you think that equals to? 4, right? How do we get to that result? Right, I can take all the steps. I can say, well, square root of 4 equals 2, and we're still carrying the square. Or that's right, these two kind of kill each other. They're opposite operations, right? In the same pile. So if I ask you what is square root of 5, which is irrational number, but squared, you will just say, that's just 5, because these two will get rid of each other. You're taking the square root, and then you're squaring it. Does that make sense? Well, let's think about this. What does the square root of 5 tells me? Square root of 5 gives me a number such that if I square that, I'll get 5. Right? That's what square root of 5 means. Square root of 5 equals a number, so that if I square that, I'm going to get 5 by the definition. And then I'm squaring that number, so I should get 5. Yeah. If I get all down and dirty with that and actually plug it in the calculator, which I shouldn't, that's the square root of 5, and then I'll square it, I'll get 5 back. But again, this is the idea. The square root of 5, by definition, square root of 5 equals a number such that if I square that number, I'll get 5. That's the definition. And here I am squaring that number, so I should get 5. Or just take it as a rule, if you have a square root of a number and you square it, you're going to get that number back. Doesn't quite work the other way around. If you take a square root of something squared, you have to be a little more careful. We'll get into that a little in a little bit, but not today. But this is kind of a general rule. If you square a square root, it gets rid of the radical. Okay. So at the same time, if I take number like 2 square roots of 3 and I square that, the whole number. Now remember, 2 square roots of 3 means 2 times the square root of 3. And when you square a product, you have to square each item in that product. So that just simply becomes 2 squared times square root of 3 squared. By the rules of exponents, right? I mean, you do have this rule of exponents that says ab to the power n equals a to the power n, b to the power n. So if you have a product, you can distribute the power. So that gives me what? What is 2 squared? 4, and the square root of 3 squared? 3, so overall, 12. Is that okay? If I take negative 5 square roots of 7 and I square that, again, I have to square both numbers. I'll have to square negative 5, and then I have to square 7. 25 times, well, the square root of 7 squared. So 7, right? So 175. Right? Now, but how about this? If I take number like 2 plus the square root of 3, and I'll square that. What do you think that will equal to? Yeah, we'll have to use our formula. We're trying to square a sum. Every time you square a sum, you have to use our square root of a sum formula. So that's the first squared plus the double product plus the last square. So that formula still holds because I'm squaring a sum. Every time you're squaring a sum, doesn't matter what the sum is, that thing shows up. So 4 plus 4 square roots of 3 plus 3, right, if I actually compute that. And now the rest is just like combining like terms. I have 4 plus 3, so that's 7 plus 4 square roots of 3. So that's what that'll be. I can actually combine 4 and a 3 into 7. And 4 square roots of 3 is 4 square roots of 3. Nothing else I can do about it. Yeah, again, I don't care what it is in decimals. That's my answer. Yeah, just leave it like that. So every time you're trying to square a sum, no matter what that sum is, you got to use the formula. Okay? At the same time, if I do something like that, 2 plus square roots of 3 times 2 minus the square root of 3, I can again use my formula, because that's the difference of squares, right? They have identical terms that only differ by a sign in the middle, so that becomes 2 squared minus the square root of 3 squared, using the difference of squares formula, which is 4 minus 3, which is 1, right? Is that okay? So, see what happens. I took, in this example right here, 2 square roots of 3 is an irrational number, okay? I can never write it as a fraction, as a ratio of 2 integers. It's just ugly, it goes on forever. But I took that number and I squared it, and I ended up with something very friendly. I ended up with an integer, which is rational number. So I took irrational number, I squared it, and I got rational. Same thing here. I took irrational number, I squared that irrational number, and I got rational number back. You see that? Start with the rational squared. 175 is an integer. It's a rational number. While here, 2 plus square root of 3, that's irrational number. It's something. And I squared it, and I still got irrational back. Okay? So simply squaring irrational number not necessarily gets rid of. Right. So we see it didn't happen here. But when I multiply two numbers like that differ by a sign in the middle, the answer will always come out to be rational. Because look, no matter what two numbers I choose, let's play this game. Give me a number that kind of looks like that. 4. Square root of what? 5? Okay. And if I multiply it by 4 minus the square root of 5, the result will come out to an integer. I'll get an integer for the answer, because this will be 4 squared minus square root of 5 squared. Automatically by my formula, so that's 16 minus 5, so 11. Okay? And I can make it really ugly. I can take things like, 8 square roots of 3 minus 2 square roots of 5, something like that. That's a badass irrational number right there. Okay? There are many irrational numbers. I can always do that. I'm going to say something really weird right now, and I hope you'll survive that. But how many do you think there are rational numbers out there? Infinitely, right? How many do you think there are irrational numbers out there? Infinite, right? They're both infinite. Did you know that? But there are many more irrationals than rationals. We can actually say that. The size of this infinity just completely dooms the size of that infinity. It's just weird, but we can actually compare infinities. This one is much grander infinity. I know, that's weird, right? I can actually, I'm not going to get into the details, but I can almost count them. I can almost put my fractions in order. I can come up with a way to say, you're going to be the first fraction, you're going to be the second fraction. I'm not saying that you're bigger or smaller. It's going to be, I won't be able to do that. But I can at least put you in some kind of a weird order all the way through all of them, really. I won't be able to do it with those guys. It will fall apart. So there are different categories of infinity. Like this is a countable infinity. I can still please say, okay, you're the first, you're the second, you're the third, and so forth. Well, in this case, it's just chaos. So
there's more symmetry in the top, it's easier to define down here.
not really, but it's weird. So never mind. I'm just saying. So some irrational numbers, I can get really, whatever I piled things up, and it just has square root of 3, and it just automatically makes it irrational. But anyways, if I multiply this by the same thing with an opposite sign, I'll end up with rational number in the end. I can use my difference of squares formula to say this is 8 square roots of 3 squared minus 2 square roots of 5 squared. And then I'll just perform the operation. Remember how we did that? The square will distribute through the first one, because it's a product. So what is 8 squared? 64. And what is square root of 3 squared? 3. So it's 64 times 3 minus 2 squared. So that's 4. And square root of 5 squared, 5. So this is 192 minus 20, so 172, right? Which is an integer, so it's rational. Okay. So in general, the numbers that differ by a sign in the middle like that, we'll call these numbers conjugates. If you have two numbers that differ by just a sign in the middle, we'll call them conjugates. Yeah, right. So if one has a minus and the other one has a plus, and they're just everything else is the same, we'll call them conjugates. And every time you multiply two conjugates, you will utilize the difference of squares formula. And when you have conjugates that involve square roots, it will always come out to be an integer. Could be negative integer, but it will be an integer. Well, it will be a rational number at least. Okay, so the product of conjugates will result in a natural number. I'm sorry, will result in rational number. Okay? Because eventually we're going to, as I said, we're going to really discriminate against irrational numbers. So we're going to be looking for the ways to kill them, and there's one of them. Use the conjugate thing. Okay? Well, anyway, so, but for now, you should be doing pretty good, I think. It's square roots. You've seen them before. So I have a worksheet for you. You can have a lot of fun with it. Yeah. Have some fun with it.